So we're in the external flow section, and last time we did flow over a flat plate. And if you remember, if it was laminar, we could do a Navier-Stokes equation solution for the laminar, but if it was turbulent, we had to go to experiments. Now if it's any other shape besides a flat plate, you pretty much cannot do the Navier-Stokes equation. So we don't even distinguish between laminar and turbulent. We just go ahead and do the experimental results like we did for the turbulent flow over a flat plate. And what that means is you find the coefficient of drag, and you're going to do that using tables, figures, equations, any way you can. And once you find that, then you can solve for drag using this equation. So your drag is just going to be CD times 1/2 rho v squared a. All right. A lot of times you have to use a free body diagram. Maybe gravity is causing your object to move, or who knows what. So a lot of times you have a free body diagram that you have to work with. And then you can use your drag that you got from your CD. So one of the questions you have here is this A. What is this A? And this A depends on really what type of drag you're going to have mostly. So if you have some kind of blunt object, usually pressure is going to cause most of the drag. And so in that case, you're going to use what's called the frontal area. All right. And the frontal area is basically what does the wind or the flow see? If you were standing right in front of this car, for instance, what would you actually see, assuming you can't see any depth? And what you would see would be, well, you'd see little wheel wells here, and the main body of the car, and the top. That's what you would see. So that would be the area that you would use for that car. All right, so that's the frontal area. The other kind of area that you could possibly use is called the planform area, and you would use that whenever shear is the main cause of drag. Okay, so you got a big surface area where the flow is going parallel to the surface, like in a wing. Okay, for instance, this great big, whatever that is, airplane with a gigantic wing. In that case, what you want to use is what's called the planform area, and that's basically the area that's exposed to that shear. It's what we used with a flat plate. So in this case, you would look from above, and you would just get a top view, basically. And that, in this case, would be a rectangle. Okay, and that's called the planform area again. Okay, another type of area that could possibly be used is the wetted area. So for example, if you have a ship or a boat and it's plowing through the water, maybe it has a frontal area like this. This part of it up here, this is a boat, this part above the water is not going to experience a whole lot of drag. It's mostly going to come from under the water. So this is the area that you would use. Okay, so these cases that I showed you, those were pretty obvious as far as what type of drag occurs in each case, but it's not always obvious. So you just need to know what was used when the CD was calculated in order to know which one to use. Okay, you can guess a lot of times if it's obvious what type of drag is most important, pressure or shear, but sometimes you have to kind of guess. For instance, here in this figure, this is like I think they call it like an elongated cylinder, something like that. So it's kind of like a wing, but this has a thickness ratio here. So if C gets really big, it gets to be more like a shear kind of flat plate kind of shape. Whereas as this goes down to 0, you get a circular cylinder. All right, so as you can see, what they've done here is a CD based on planform area and a CD based on frontal area. Okay, when you get up to this circular, and you see how they're different, right? So it's important to know which one. Circular cylinder up here, T equals C in that case. What you get is the same CD. So you have the same CD, and that's because the area is the same if it's a circular cylinder, whether it's the top view or front view. Both cases you're going to get basically a rectangle, right, if it's a cylinder with flow going over it. Okay, front, top. Looks the same. All right. So again, the key to solving these problems is finding the drag coefficient, and you find it in graphs like this above, or in tables, or sometimes it's equations, and you can come up with that. For us, for our tests, it'll be from our book, but you could also do your own experiments, or you could look online, or in literature, that kind of thing. Remember that both the front and the back matter. So because of separation, whenever you have separation like this, you're going to get an increase in drag. So the more streamlined you can make it in the back, the better. And in fact, this has the same coefficient of drag as that. The front also matters. If it's really flat, that means the flow, it's going to have to turn the flow that's 90 degrees, and you're going to get a high pressure over the whole face of this compared to this, which is going to have a lower CD because it's not going to have to turn some of that flow quite as far. All right. So in your book, there's a bunch of figures and tables, a couple of figures, which means they're graphs, streamlined cylinder above, various 2 3D smooth bodies, various 2D shapes, various 3D shapes. These are in separate bodies. So what does it, or separate tables, what's it mean if it's a 2D shape? Well, that means that, you know, you could like cut it into slices all along it like a wing, long into the page, we'll say. And we can cut into slices that are the same. So that CD chart up above, previous page, 3D shape, figure 612. Okay, so stop here and do quiz questions 1 and 2.